Now, one way to think about the fact that the standard basis generates any other vector is that the standard basis specifies a preferred coordinate system. So if you think of a vector as a geometrical object, then the standard basis provides the axis of the coordinate system, and the coefficients ci, so the entries of the vector, are precisely the coordinates of the vector in this coordinate system. However, the standard basis is not the only choice of coordinate system. One could choose a different set of n vectors, and this would change the coordinates which specify the vector. In other words, the coefficients in the linear combination that yield the vector. And so one natural question is, for example, can we use a different pair of vectors other than the standard basis to generate all vectors in 2 dimensions? So let's think about this question visually again. So in this widget, you get to choose 2 vectors. So the first one is the one in red, and this has entries a1, a2. So at the moment, a1 is equal to 1 and a2 is equal to 0. And so this is the first standard basis vector, but you can change it to be whatever you want. And so for now, let's leave the red vector to be the vector 1, 0. And we'll denote this with the letter u. Now the second vector is the one in blue, and this has entries b1, b2. And so currently b1 is equal to 0 and b2 is equal to 1. And so this is the second standard basis vector. Again, we can change the entries of this vector to whatever we want, but for now let's leave it to be the second standard basis vector. And we'll denote the blue vector with the letter v. And now you can use u and v to generate other vectors via linear combinations. So you get to choose the 2 scalars, the 2 coefficients in the linear combination. These are alpha and beta. So here, for instance, you can set alpha and beta to whatever you like. And the vector in green, which we'll denote as z, is the linear combination obtained as alpha u plus beta v. Now, in this particular case, u and v are set to be the standard basis vectors. So for instance, if we wanted the green vector z to be the vector 5, 3, all we have to do is to set alpha equal to 5, of course, and beta equal to 3. And of course, you can obtain any other 2-dimensional vector using the 2 standard basis vectors in a similar way. So now let's reset alpha and beta to 0. Now let's try to pick different vectors. So let's change the second vector. Let's make it be the vector 1, 1 instead of the vector 0, 1. So you can see the blue vector has changed. And now you can see that again we can play with the coefficients alpha and beta in the linear combination. And this will give us different vectors z. So for example, let's say that we wanted the green vector z to be again 5, 3. Then we can sort of try to guess coefficients alpha and beta that get us to the vector 5, 3. Let's see what we can do here. So we want to get more or less to 5, 3, which is the point here. And so let's see if we can get it more or less. Okay, that's close enough. And so you can see even with this different pair of vectors, we were still able to obtain the vector 5, 3. And if you play enough with the coefficients alpha and beta, you'll start to get the sense that actually any 2-dimensional vector can be obtained as a linear combination of these 2 vectors here, 1, 0 and 1, 1.